right, so my name is Matt Calvert. I just finished my master's degree in the Raglan Lab at the University of Colorado, Denver. So today I'm really excited to have the opportunity to share with you some of my thesis work on the genomics of multiple trait relationships and how that influences our ability to predict evolution, right? And so like lots of people in this room, us in the Raglan Lab are really interested in this idea of being able to identify and describe the genomic basis of adaptation, right? And we're interested in that idea because we want to use that information to assess the sort of repeatability and predictability of evolution, right? And this is something that's been addressed in lots of sort of popular systems, right? Stickleback finches, deer mice. And in these sort of tests of this idea, they found that selection on a single trait that's maybe controlled by a handful of genetic loci is actually highly repeatable across time and across space, making it sort of predictable as well, right? But studies that have addressed this sort of in a polygenic context, that means traits that are controlled by many hundreds to potentially thousands of loci, are not quite as predictable. But lots of studies have still tried to address this, right? And the way that they have done that is, one way is to sort of do selection resequence studies in the laboratory, or do trait association mapping studies in the laboratory, and then compare that to variation that you observe in natural populations, right? Another way that researchers have been doing it is just by looking for parallel variation across many populations all diverging across geography. And recent studies have used short-read genomic data to address this, right? And what's interesting is that a lot of these studies, even in a polygenic context, have seen a high degree of convergence at the level of the gene, right? But when you dig in a little bit deeper, we see that related to the nucleotide level or the allele level, we see that convergence sort of goes away, and that allele frequency changes and allele frequency differences between populations are less predictable there. And so our lab, you've been wondering, or I guess, back up. So to answer sort of our larger question, how predictable is evolution in a polygenic context? Well, it's high at the gene level, but it sort of dissolves at the level of the allele or the nucleotide. And this is something that's been demonstrated in a fair number of genomic studies recently. And so we were wondering about why this could be the case. Why are allele frequency changes so unpredictable? And there's lots of different reasons. Maybe we're missing some trait axis, maybe it's epistasis, maybe we're just genotyping a marker that has a weird linkage relationship with the actual target of selection, and maybe there's just different polygenic combinations of alleles that produce similar trait values. And so we're most interested in this question. Are we just simply failing to measure some trait axis that is influencing these allele changes, right? And this is sort of a fairly straightforward idea, right? We can think about how ecological adaptation probably involves selection along multiple ecological axes, and therefore requires response along multiple ecological traits. And so if we were to steal an example here from stick insects, maybe an example we're familiar with, adaptation to a new host plant in that system requires maybe changes at the color morph level so that you're more sort of resistant to predators or more invisible predators, and then also requires some physiological adaptation to detoxify the plant that you're trying to eat, right? And so where this might influence our ability to predict evolution is if the genetic basis of these traits are sort of non-independent, or they're related to one another, right? And so this can happen through pleiotropy, it can happen through linkage, but the main thing is that if these architectures sort of favor a trait relationship that's beneficial in our new environment, then that can really facilitate adaptation. But if it promotes trait relationships that are antagonistic in our new environment, then that can greatly influence and potentially mess up our ability to predict evolution, driving allele frequencies in ways that we weren't previously accounting for. So this brings up our major question. Is selection on linked or pleiotropically acting loci responsible for these patterns and unpredictability of allele change that we've been observing in recent genomic studies? In other words, are we just simply failing to measure some trait axis that could be influencing the genetic pattern of adaptation? And so we're going to use Ragley's, or we have used Ragley's polynomial to address this question. They're a super cool system because we know, we're fairly confident in some of the traits that are responding to selection. We know that there's more than one of them. And so these guys are native to North America, and their host fruit, their ancestral host fruit are hawthorns. And sometime in the last 200 or 300 years, they switched to being on apples, right? So the population branched off the pollen and specialized on apple. And it's important to note here too that there is a high degree of gene flow between these two populations. And this is critical because essentially any genetic variation that is sort of neutral, right, is going to be homogenized by their effective gene flow. And anything that is adaptive should be relatively easier to identify in a genome scan or in a trait association mapping study. And so the two traits that adapt these populations to their host fruits relate to life cycle timing. And so these flies spend most of their life in a state of pupal diapause or state of developmental arrest. And then they emerge as adults in the late summer, early fall to utilize their preferred host fruit. They lay eggs in that fruit. The next generation will eat the fruit, go into the ground, enter their diapause, and repeat the whole life cycle. Now the apple population, the newly formed population, has essentially shifted its entire life cycle earlier. So it can infest its preferred host, which fruits earlier in the year on average than the hawthorn. All right, so the consequence of this is apple flies are terminating their diapause earlier on average than the hawthorn population. And because of that, the next generation of the apple population is also entering the soil and beginning its diapause, where conditions on average are relatively warmer. And it's important here to note that when you take a pupa that is about to enter its diapause and expose it to warm conditions in the laboratory, it has a tendency to revert that diapause entirely. And so you can imagine in nature how this would result in extremely low fitness because you'd be emerging when there's no host fruits and there's no mates available. So we think that there's a selection pressure here on this diapause intensity. We expect that this apple population should have a high diapause intensity, should be resistant to that warming. And so a lot of recent work in Regulus pomonella at the genomic and genetic level has evaluated the relationship between diapause termination and host population differentiation. And some of these studies, by essentially looking for a genetic variation between early and late diapause terminating individuals, have found that these loci strongly distinguish host populations, but they go in the wrong direction. So we're seeing a strong association between this trait and population divergence, but it goes in the wrong direction, such that the apple population has more late diapause termination associated alleles. Now this doesn't make sense, right? Because the apple population is terminating its diapause earlier. We know that from field studies. So needless to say, this left us really, really confused. So we wondered if maybe diapause intensity or selection on diapause intensity could be explaining that strange pattern that we see in diapause termination. So we dug up that data from that paper a couple years ago, and we did another trait association mapping study for that diapause intensity trait, essentially looking for individuals who have a really high diapause intensity, who are resistant to that warming, and individuals who have a lower diapause intensity, not as resistant to that warming, right? And we did a RAD-seq approach, and we found that about 7,000 SNPs were shared between these two experiments that we could cross-compare there. And so it's important, so the main result is that intensity loci seem to distinguish those populations, and it goes in the right direction such that we see that more higher diapause intensity associated with the apple population, right? So on the y-axis we have allele frequency differences between high and low diapause intensity, and then here we have differences between apple and haw. And I recognize that this association is fairly weak, right? But it is significant, and if we look at it a little bit closer and like maybe look at just chromosome 3, we can see that association gets stronger. So we're confident this is a real association between diapause intensity and post-population differentiation. So if we look a little bit further across the whole genome, we can look at different chromosomes and our different sort of linkage groups, and we can see that there's a lot of clustering of loci associated with diapause intensity sitting on chromosomes 2 and 3 and on chromosome 5. And if we look at the older study on diapause termination, we also see quite a bit of clustering on chromosomes 2 and 3, providing a first piece of evidence that maybe these two traits are actually strongly related to one another. So we're going to focus a little bit on the associations on chromosomes 2 and 3. First, I'm going to show you variation on chromosome 1. So this is just the scatter plot of all the loci that we genotyped. And so the colored loci are those that are on chromosome 1, and then our linkage groups. And so here on the x-axis, we have allele frequency differences for diapause termination, y-axis for diapause intensity. We can see on chromosome 1, most of the variation only really is associated with diapause termination. This will become important later, so just sort of file that away in your back pocket. Chromosome 2, we see a super strong association between diapause intensity and diapause termination, which is pretty cool. We see a similar pattern on chromosome 3. So what this really shows us is that the associations between diapause intensity and termination are quite strong, and that suggesting that these traits may be actually strongly related to one another, right? And so maybe selection for diapause intensity, which seems to be going in the right direction in the apple population, could be explaining that weird variation that we observed for diapause termination, right? And so we began to wonder about why this trait association maybe even exists in the first place. And so we collected samples, well, I mean, the people in our group collected samples across the Midwestern United States, And we came up with this hypothesis about how selection might favor certain trait combinations across the range. Right, so in the hawthorn population, so in the south, growing seasons are going to be longer and winters are going to be milder. And because of that, so in our sort of southern populations, we expect a higher diapause intensity, and we expect later diapause termination. And these trait associations sort of are linear as you go further north. We'd expect lower diapause intensity and earlier diapause termination. Now, it's important to mention that long-term historical selection should favor genetic architectures that promote these trait relationships, right? And so in the apple population, we're actually selecting for, natural selection is selecting for populations that are sort of perpendicular to this axis of variation, or our hypothesized axis of variation, right? Such that at each location, the apple population should be having a slightly higher diapause intensity because it's going to the ground earlier in the year, and it should have an earlier diapause termination, right? So we have this potential perpendicular selection, setting us up for a potential antagonistic relationship here. Okay. So we keep our sort of hypothesis right here. I'm going to show you frequencies on the x-axis, frequencies of high diapause intensity alleles, on the y-axis, frequency of late diapause termination alleles. And we can see that the variation across the range sort of matches our expectation, at least at the genetic level. What's interesting is that the hawthorn or an apple population, we see things moving in the right direction for that diapause intensity allele, but it seems to be at the expense of variation in diapause termination, right? It's almost as if we're dragging along that variation, that maladaptive variation with it. You see a very similar pattern on chromosome 3, and I'll wrap up just a second. And this brings up, so basically the main thing here is just that long-term historical selection has sort of produced these trait correlations that are contemporary to selection, at least at the genetic level, antagonistic to contemporary selection. And so remember earlier I showed you that chromosome 1 really seems to only be associated with diapause termination. And so we can see here that the graph has shifted a little bit. Now we're just looking at across sites, and just we have frequency of that late diapause termination associated allele. We can see that variation sort of still moves in the wrong direction, north in the range, but as we move south, variation starts to go in the right direction, such that we see fewer of those late diapause termination associated alleles in the apple population. And so what this has allowed us to develop is sort of this mechanistic model for adaptation. By combining these trait association mapping studies with genome scans for selection, we've developed this new hypothesis that we can test in the future, or maybe antagonistic selection on chromosomes 2 and 3 through pleiotropy or linked selection is dragging along potentially maladaptive variation and diapause termination, and that could be being compensated for on chromosome 1. So with that, I'd just like to acknowledge my committee members, everybody here who, so many people in the room who helped out with this work across all of our collaborating institutions, and I can take any questions with the time we have left. Thanks.